Now that we've looked at normal stimulus and response for HTTP, we're going to turn our focus to abnormal SNR, and really we're going to focus mostly on security scenarios here. We've already talked a little bit about response codes with HTTP and how you can get back error codes, internal server error, 500, things like that. We're not going to focus on that too much because I feel like that's pretty self-explanatory from what we've seen, and those codes are generally pretty descriptive. So we're going to focus on security. We're going to get even more into security later with a dedicated section, but we're going to talk about a couple security-related abnormal SNRs that you'll see for HTTP, starting with malware C2. So when I say C2, I'm talking about command and control. And in this case, I want you to put yourself in the shoes of an attacker. You've infected a system with a piece of malware, and you need to communicate with that system via the malware, right? So you could go through a bunch of effort, write a custom protocol, custom command and control channel, and try to make it where it blends in and it's hidden amongst all the other communication coming to and from that host. Or you could just use HTTP because it's already a protocol that's flexible enough that will allow you to do that, and you don't have to reinvent the wheel, and it'll be hidden amongst other HTTP traffic, and it'll be harder to spot. And that's what a lot of attackers do. As a matter of fact, HTTP is the most common and most prevalent command and control channel used by malware by a long shot. So there's a number of reasons, another types of communications that can be facilitated with HTTP. You can configure it to post system information outside the network, to poll for commands for some type of backdoor, anything like that. It doesn't really matter, but it all falls under the umbrella of command and control. So in an example, let's consider this. We have System A, which is a victim machine. It's a machine that's been infected with some type of malware. And we have System B, which is the attacker's evil C2 server. And now that System A has been infected through some mechanism, we want it to communicate with System B. Well, to do that using HTTP, very simple. And there's a number of ways to do this, but most common what you'll see is some type of request made to the evil system. It can be a GET, it can be a POST. In this case, I've just chosen to make it a POST to /dev/ID equals 123. 123 would be any number of information. It could be an IP address, some type of encoded system information. A lot of times it'll be base 64 encoded or some other type of encoding there. But the critical thing to notice here is the user agent. When you look at that user agent, you're going to look at it and say, okay, this seems legit, right? It's a Mozilla-based browser. It looks like it's running on Windows. However, what you don't notice there is that that's actually a known malware user agent made to look like a legitimate one. So if you're just looking at a list of user agents on your network and you see this, you might say, okay, that one looks legit. But it's actually most closely associated with Sality, which is a pretty popular piece of malware that exists out there. So this is actually malware C2 in this particular case, but it looks kind of normal. It hides amongst the noise, and that's one of the reasons attackers are wanting to use HTTP. Not only that, as I mentioned before, you can make the user agent string anything you want it to be. Browsers obviously have common things associated with them, but you can spoof that. You can write your own code and your own scripts that sets a user agent to whatever it needs to be, including something that it is not. So keep that in mind, that because HTTP is so malleable in this way, it can be used for a lot of purposes. And this is an example of how it might be used for command and control. And there are lots of examples out there for that. If you just do a Google search for HTTP malware, you'll find a ton of things. We'll go through a couple examples of that later on in the security section of the course, where we'll actually trace infection chains from common pieces of malware, and many of them will use HTTP. So I say this here to get you prepared for that section, that HTTP is a very common method, and it falls under the falls under the category of abnormal stimulus and response when it relates to the hypertext transfer protocol. The next type of abnormal stimulus and response, and really the next couple types we're going to talk about, all fall into the category of request input manipulation. So actually taking the request we're sending to a web server and making specially crafted requests that cause very specific things to happen, generally taking advantage of flaws or vulnerabilities in the HTTP server or the code running on it itself. And that's a whole class of vulnerabilities. Remember when we talked about Wireshark, one of the things that was interesting about Wireshark is because it takes so many different types of data, and there's so much variability in the data and how it has to parse that it's really susceptible to a lot of different vulnerabilities. And that's true of any application. The more different and varied types of data you take as input in different ways, the more susceptible you are to vulnerabilities, because vulnerabilities usually exist in the parsing of that data and how it can be escaped and manipulated to access things that you really don't intend for people to access. So that covers a whole class of vulnerabilities related to HTTP communication. This is where we get into things like SQL injection or cross-site scripting. That's another one. And also the one we're about to talk about now, HTTP directory traversal. So I'm going to show a couple of examples of those. We'll talk about directory traversal, and I'll also talk about SQL injection and show you some quick PCAPs of what those look like. Both very different vulnerabilities, but both the same type, and that they have to do with the manipulation of input parameters or request parameters coming to the HTTP server. So let's actually look at HTTP directory traversal first. Now, in this case, we have System A, who is an attacker. It's a bad guy. We have System B, which is a legitimate web server. In this case, System B is running a web server. Let's say it's Apache in this case. And Apache is configured with a specific user account that only has permission to access the Apache web root. So the series of files and folders that you want shared out over the internet. That's all it can access, and that's all we want it to access, because that's all we want users to be able to access when they interact with it. However, let's say that server is misconfigured and that user account actually has the ability to access files all over the system. Like, let's say it has root access to the system, can access any file on it. Now pair that with an input vulnerability in the code of the website being delivered that allows users to request arbitrary files. And that's where a directory traversal attack will manifest, and it will often look something like this. In this case, the attacker is sending us very specially formatted GET requests where we have a couple different things going on. First, we see several iterations of .. If you've spent any time on the command line, you know that you use .. to browse a directory up from where you are. So if you're in /folder1 /folder2 and you say change directory .. you will go from folder 2 to folder 1. So what we're doing here is inputting many .. So moving up all the way up, it looks like 5 directories here, which in most cases is probably going to get you to the operating system root directory. At which point we have the etc directory, which contains the password file. Password on most modern Unix systems doesn't actually contain passwords anymore. We have the shadow file for that. But traditionally, an older Unix system, this would contain all user accounts and passwords. In this case, we're just talking user accounts for the modern Unix systems. Nonetheless, what we're doing here as the attacker is taking advantage of a specific type of input field in the code running on the web server, and the fact that the web server is misconfigured itself, and browsing to the etc password file. So we're browsing outside of the safety of the garden of where the web server wants us to visit, and going up and grabbing this additional file. And this is just an example. If we can grab this file, we can probably grab any file on the system. And if we can grab any file on the system, we can do some damage. That's where we can get also the etc shadow file, try to do some password cracking, things of those nature. Now, in a normal scenario with normal stimulus and response, if I tried to make this request on a web server, I would get a response back that said 403 forbidden or something like that. It wouldn't return the data. But in this case, for abnormal stimulus and response, since our web server is misconfigured, we actually get an HTTP 200 OK back, and we're actually going to get the contents of the etc password file delivered right back to us. And that is a very, very bad thing. So let's actually take a look at this at the packet level so you can see what I'm talking about. I've opened up a file called HTTP DVWA directory traversal. And DVWA is an important acronym because it stands for Damn Vulnerable Web Application, which is a free open source web application you can download and deploy that's inherently vulnerable to a lot of different web-based vulnerabilities. So you can actually attack it and certainly learn offensive concepts, but you can actually sniff the packets while you're doing it and learn how to dissect those packets and what those attacks look like as well. So we'll actually use a few different packet captures I generated from attacking that application throughout the course. And this is the first one wherein we'll look at a directory traversal attack. Now, in this case, you'll see my source IP address is 10.2.101 and my destination is 10.2.2.104. 101 in this case is the attacker. This was me in this scenario. And 104 was the web server running the DVWA application. So we see our three-way TCP handshake right off the bat. And then we immediately see a GET request. And this GET request is where the magic is happening for this directory traversal attack. Now, if we look through this GET request, pretty much everything in here is normal. Everything in here is legitimate and perfectly okay. We see cookies, we see accept encoding, user agents, and so on. These are all legitimate. It looks like this was done via Chrome, which I can say was the case. Chrome on a Mac MacBook Pro. And really the only thing that's different here is this GET request. And it's a perfectly fine formatted GET request. Everything is as it should be. There's no protocol anomalies here. The only thing that's weird is the nature of what we're requesting, right? So that's what we mean when we say it's a input or request vulnerability. It's just what we're requesting is causing a very specific thing to happen on the server that is undesirable from the standpoint of the good guy, very desirable from the standpoint of the bad guy. In this case, I'm requesting /DVWA/vulnerabilities/FI/?page equals ... so on and so on, etc password. So what we have here is the server has an input on it, and it's this input of ?page equal, and it allows you to include other pages, ideally within the confines of what the web server administrator wants you to pull up. So it includes other pages on the web server. However, it's misconfigured, and it's actually letting me access any file on the system, and the web server is running under a user account that can also access any of those files. So I figured this out as an attacker, and I'm going to take advantage of it, and I input this string to download the etc password file. Now, if this were properly configured and this wasn't possible, we would get a response back saying something like, 403 forbidden, or maybe even a 404 not found, depending upon the configuration of the server. But here, that's not what we get back. We see a couple packets later, we actually get the 200 OK. So that's occurring after a TCP ACK and after another packet containing data. This is split across two packets here, around 2,000 bytes. And we're actually getting an HTTP 200 OK, which means this was at least accepted. And the question becomes, did we get the data we're looking for? Did we get that file? The best way to probably figure this out is just to follow the HTTP stream. So I'm going to right click on this packet, go to follow, and look at HTTP stream. Sure enough, up at the top, we see our request. And if we look at our response, the very first thing we see is the contents of the etc password file. That's what we're looking at right here. So this file was actually dumped and transmitted over the web, clear text for anyone to see. And we can actually see user accounts here. Looks like we have most of the default Linux user accounts. But we also have one for MySQL, and we also have one for Sanders, for me. So it's actually dumping all of those user accounts, all their information right here. No passwords. Those aren't in the etc password file here. But there's nothing to stop us from going after the etc shadow file as well. If we can get to this one, then we can probably get to that one. Now after that, you actually see the actual HTML content of the website. So we see all that. We see HTML starting here. We see all of the normal HTML tags that are available. So this is actually being dumped ahead of the page that's also being sent back to us. So in this case, this was a successful attack. Normal HTTP being used as it's intended, but the input parameter that was sent over HTTP was something that caused the server to produce a very undesirable response, resulting in successful exploitation of a directory traversal vulnerability. The last type of abnormal stimulus and response I want to talk about for HTTP is really just another example of an input or request manipulation that causes an undesirable action to happen on the server, and that's going to be SQL injection. So when I say SQL, I mean SQL, the structured query language, which is used to query databases. Now, here we have System A, which is our attacker, System B, which is our web server. Generally speaking, in normal architecture, web servers often communicate with database servers. Web servers deliver and present the information, whereas database servers contain data that is then shared back through the website, through the web application. The general goal is that the web server interacts with the database server, and the browsing sites, so the clients, never interact with the database server directly, and we certainly wouldn't want them to, because then they could perhaps access data they shouldn't be accessing, or even manipulate data. So that's what we don't want. Now, in this case, we have System A, we have System B, and we're going to send a very specially crafted command. And it says get/directory/?ID equals, and then some stuff that doesn't really make a lot of sense, right? This looks kind of just like a bunch of mess. Well, what we're doing here is actually manipulating the ID parameter on the page we're interacting with. And that can be via some type of form. It may be directly via the URL. But all that's important to know is that the ID parameter takes some type of input. Maybe it's looking for a user ID, so it can output information about a specific user. Maybe it's a website about books, and you put in an ID and it will pull up the information about the book. Well, in this case, we're manipulating it by using this percent apostrophe or 0 equals 0 to break that form essentially and output the list of all of the IDs instead of just one. So if this is a user database, we're going to get all the users. If it's a book database, we're going to get all the books. It's going to dump all that onto the screen. Now, ideally, the web server is configured such that it will prevent this from happening by filtering specific types of input and also maybe doing some output filtering as well. However, in this case, that's not what's happening. And we're going to show you that in a packet capture in a minute. But in this case, the system responds with an HTTP 200 OK and actually sends that database information back to the user. Now, you may get a 200 OK even if this fails, and most of the time you probably will. So that's kind of irrelevant to the response portion of this. I want to show you the response, though, in a packet capture because that makes a lot more sense. Now, real quickly, before I show you the packets for SQL injection, I think it helps to actually see the attack in practice before I do that so you can see actually what's going on. So I'm going to show you this attack and then show you the packets that were generated from it so we can then understand that at the packet level. And we'll do a lot more of this type of thing on in the security section, but I do want to do this now for this SQL injection vulnerability. Now, in this case, I've opened up DVWA, again, the damn vulnerable web application, and I'm on the SQL injection page. And this is where you can actually take advantage of a SQL injection vulnerability. Now, in this case, we have this user ID field, and this is meant to input a specific unique user ID to get information about a user, ideally maybe your own user account, so you can get your own information that you can edit. In this case, I know, let's say I'm user number 2, so I enter my user ID number and get my first name and last name, which in this case would be Gordon Brown. But what if I wanted to manipulate this field? What if I knew it was vulnerable to SQL injection and wanted to manipulate it such that I could get a list of all the users of the system? Well, that's something I can do. So let's do that now. So to do that, we're going to put in a specially crafted command that I know will break this form, that I know will allow me to accomplish what I'm trying to accomplish here. In this case, it's percent. Well, you can read it right there. This is the command that we're going to use. Now, if I hit submit, look what happens. We get all of the user information. So we see the admin user, we see the Gordon Brown user, Hack Me, Pablo Picasso, and Bob Smith. We get all of the users on the system. Now, just imagine if this particular table had password information. We could get that too. Now, this application does actually contain password information, and you can use this same vulnerability in a slightly different way to get that password information as well. We're going to save that for later for you in a lab exercise. But you can see how SQL injection works. It's just a matter of manipulating the input that I'm sending to the user and then, to the web server and hoping that a vulnerability exists if I'm a bad guy so I can exploit it. Now, also take note that as we were manipulating these variables, the command appears up here in the address bar, right? We have URL encoding here, so that's when we see things like %25, %27, and these pluses, so it can actually exist in the URL bar, and that's important as well. But those change as we manipulate this. So we don't even have to actually interact with this form. We could just manipulate up here directly. But nonetheless, this is the example of the SQL injection vulnerability that I'm about to show you the packets for next. You're now looking at another packet capture from DVWA, the damn vulnerable web application. And this one's called HTTP DVWA SQL injection.pcapng. And it shows a couple different examples of SQL injection going on. So we have a few of them in here. I'm only going to go through one real quickly, and you'll actually look at another one in a lab exercise. In this case, we have two hosts again, 10.2.2.101, which is our attacker in this case, and 10.2.2.104, which is our web server. We have our three-way handshake to set up the connection, and then we see the GET request that's going to be of interest to us. Now, again, everything in this GET request is perfectly okay, perfectly legitimate. The only issue lies in the request URI here that contains information that is something we don't necessarily want to see. In this case, we're making a request for /DVWA/vulnerabilities/SQLi/?ID equals, and then we see this stuff. Right? Now, there's a couple things going on here. This is pretty darn similar to the example I just showed you on the slides. However, the thing to note here is that we see these things like %25, %27, %27. That's actually URL encoding, right? So we can't. There's certain characters we can't just have in a packet or can't have going across the wire because they'll mess up the way that data is input and exchanged. So instead of things like tick marks like parentheses, apostrophes, spaces, etc., we see URL encoding. So we see things like %27 instead of spaces. We see these pluses. It appears a little bit differently at the packet level when you look at it. So you'll get used to seeing that here, and it may help to go ahead and parse this out if you want to see it a little bit more cleanly. So next, let's go ahead and look at the response that comes back to understand what we're seeing there. If I go ahead and click on the HTTP 200 OK, we do have an OK response coming back. And I'm going to go ahead and follow the HTTP stream here. That's often the best way to look at this data in a reassembled, easy to understand way. Now, in this case, we have a lot of legitimate HTML. The page came back to us as it normally would, and the extra information we're going to be getting is going to be given back actually in the context of this page. So I'm going to scroll down a little bit, and I think somewhere, here we go, right around here. This is where we're going to see the interesting thing. Here's our command we input. Remember, ID %, 0 equals 0. We set that to always true, so we're going to get back all the usernames. That's what we wanted. And sure enough, we have them. Look, first name admin, surname admin. So we're getting that information. First name Gordon, surname Brown. First name Hack, surname me. So this is actually a list of all of the users of the application, whereas the form was designed to only give you information about one user, maybe a user you knew, maybe a user ID you knew, maybe you're entering a password along with it, but in this case, just an ID. It's only supposed to give you one, but by manipulating that, doing the SQL injection, we're actually getting back much more information. We're directly interacting with the database, manipulating that in a certain way to get more information. Now, this is a pretty benign example. We could use this to manipulate a lot more things, right? We could go get passwords. We could actually go get the passwords for these accounts. That's something we could do if we have this access to the database. We could maybe even insert our own account, insert an account with our own username and password and use that to access the application at a higher privilege level. The sky's really the limit depending on how we can access this particular service. But again, just another example of how HTTP input can be manipulated to interact with the web server in an unintended way. That's really the crux of the issue with all of these HTTP request type things. Again, not abusing the HTTP protocol itself, but using it as a carrier to abuse the HTTP server on the other end. Very common type of vulnerability. You'll see it a lot. SQL injection, cross-site scripting, all these things are incredibly prevalent even today.